which will be taken by before we start this lecture sessions here. It is customary for us to have a brief introduction to the course and welcome the participants. So I'll first request Professor Srinivas, Head of the Department Mechanical Engineering, to welcome the participants to this particular course. Professor Srinivas, please.
Thank you, JP. Dear course faculty, Professor Anastasios P. Vassilopoulos, Ecole Polytechnique Faculty, Lausanne, Switzerland. Our Director, Professor Vinod Kumar Kanodia ji. Course coordinators, Professor Raman, Bedi and Professor SP Singh. Faculty, professors, participants, one and all. Very good afternoon to all. A grand welcome to Global Initiative on Academic Network GIAN program on life reduction methodologies and fatigue of composite materials, organized by Department of Mechanical Engineering, IIT Jalandhar. GIAN is a program by the Government of India to strengthen India's scientific and technological capacities and academic resources. The main objectives of this program is engaging the international talents, improving the academic resources, accelerating the quality reforms, and improving the scientific and technological capacities. Regarding to composite materials, they are well known for their strength, stiffness, and lightness, and have many notable advantages with the promising applications in the field of material science and mechanical engineering. We thank Professor Vinod Kumar Kanodia ji for the continuous encouragement, motivation, and the support to conduct this type of value-added programs to the department as well as institute level. The Department of Mechanical Engineering, IIT Jalandhar, was established in the year 1990 and has grown one of the dynamic departments of the institute over the last 3 decades. The department offers BTech, Masters in Design Engineering, Thermal and Energy Engineering, and PhD programs. The BTech program is accredited by NBA, National Board of Accreditation. We have a state-of-art of research facilities to support our dynamic academic and programs at the research. Faculty members have excellent academic credentials and are highly regarded. I hope this wonderful program enables the participants to apply the concepts, innovate the composite materials, and create the new products from the inputs during this 5-day program. Thank you.
Thank you very much, sir. I will now request our director, Professor Vinod Kumar Kanodia ji, to welcome the external expert and the participants to this course.
Okay, thank you, Dr. Raman Bedi. Am I audible, no?
Yes, sir, you are audible.
Okay. Yes. So, distinguished guests, esteemed faculty members, and enthusiastic students, it is my honor to welcome you to this GIAN course on a life prediction methodology in a fatigue of a composite materials being held in a virtual online mode. Today, we earmark a unique intellectual adventure, bridging up geographical boundaries and fostering global collaborations. I extend a warm welcome to our esteemed international experts, Professor A.P. Vassilopoulos from EPFL, Lausanne, Switzerland, who has graciously accepted our invitation to share his domain expertise in fatigue behavior of a composite materials. Composite materials have revolutionized various industries, including aerospace, automotive, and renewable energy due to their exceptional strength to weight ratio, corrosion resistance, and design flexibility. However, their fatigue behavior under the cyclic loading conditions significantly impacts their performance, reliability, and lifespan. This course aims to provide a comprehensive understanding of the fatigue behavior of a composite materials. This course is being organized under the GIAN initiative funded by the Ministry of Human Resources Development, Government of India, which aim to facilitate international collaborations, expertise sharing, and capacity building. This course is a testamental to NIT Jalandhar commitment to academic excellence and global partnership. I extend my best wishes to Professor Raman Bedi and Professor SP Singh, who are acting as a coordinators of this GIAN course. I hope that participants will enjoy the course and learning outcomes will be benefited for them and will also act as a catalyst of industrial growth in a country. So I think that he will enjoy and learn more from an expert. Thank you. All the best wishes from my side.
Thank you very much, sir. I now request Professor S.P. Singh, course coordinator, to briefly welcome the participants and the expert to this GIAN course.
Say good afternoon to all of you and good morning to Professor Vassilopoulos. I hope you are all fine and ready to take up the challenge. So I thank our director for sparing time and joining the inauguration ceremony. So this, as Professor Raman Bedi has told you, that this GIAN course is an initiative by the Government of India, Ministry of Education, where we engage international experts in a particular area to deliver expert lectures to the participants here. So the course objectives and the other details have been shared with all the participants. And I think that this course will be very, very useful to the participants. And I do remember that a few years ago, Professor Vassilopoulos visited this place and we had a offline course at that point of time. So it was a very nice experience and we will try in the near future to have him again in our campus. So I welcome all the participants to this course and I request all the participants that this is a very specialized course. The lectures will be very, very informative and knowledgeable. So I advise all the participants to connect in time and listen to the lectures carefully. These will be very, very useful. So I once again thank everybody who has taken interest in this course. And also I thank our director, Professor Binod Kumar Kamarjiaji, and head of the mechanical engineering, and Dr. Tangapalli, for sparing time and joining the inauguration ceremony. Thank you very much.
Thank you very much, sir. Before we start the formal session, it is my duty to introduce the speaker to the participants. Professor Vassilopoulos needs no introduction as such for those who work on fatigue of composite materials. He is a renowned expert in the field of composite materials and structures with a career spanning more than 25 years. Currently, he is holding the position as adjunct professor and director at Composite Mechanics Group at EPFL Lausanne. His research basically focuses on fatigue behavior of composite materials in various applications like wind turbine blades and other complex loading conditions. He has guided more than 17 PhD theses at EPFL Lausanne. He has authored around 120 journal articles, 4 books, 21 book chapters, and also holds 2 patents. As I already said, to the community and the fraternity working in the field of composite materials and specifically in the field of fatigue of composite materials, he needs no introduction at all. He is a very good friend of mine and we connected somewhere in 2006. And I thank him very much for accepting our proposal second time. So as Professor Singh already said that he has physically visited and conducted a similar GIAN program in the year 2019. And this time also we requested him to share his expertise through online mode, and he has readily agreed. So I thank you, sir, once again for accepting our invitation. Going through the same CV, which we say of Professor Vassilopoulos, he is on the editorial board of International Journal of Fatigue, Journal of Journal of Reinforced Plastics and Composites, and ESIS European Structural Integrity Society Journal. He is also the director of the doctoral program in civil and environmental engineering at EPFL, and he is also the president of he was the president of European Society of Composite Materials from year 2020 to 2024, where he organized ESCM for the information of the participants. Is a can say the fountainhead of academic activity and professional activities in the European Union, working on for the people working on the field of composite materials. It's a very lively and big society, and which he was heading for last 2 years. I thank you once again, sir, for accepting our invitation. Before we start the proceedings, just an introduction to the participants. We have more than 90 registered participants for this particular course. And the participants come from Academia, they are from student background. We have research scholars, we have PDF scholars, we have faculty members, and we have industry participation also. We have 2 participants from Schneider Electric India and 2 participants from DRDO, Defense Research and Development Organization. I hope Professor Dr. Ramadas may be here connected already. He again is a very good friend of mine, and he was here with us in the last session also. So with these words, I will stop here because we are coming to almost 12 minutes. We have run into the time. I will hand over the stage to Professor Vassilopoulos for taking you forward for this journey on fatigue of composite materials, and he will share with you. We have already shared the session details with everyone, and I expect that everyone will be joining in time so that we are able to conclude the sessions, and then everyone is able to take the benefit of the expertise available with the Professor Vassilopoulos, and that's the main aim of holding such GIAN programs. Thank you everyone for joining this inaugural session, sir. I thank Professor Kanojia, Professor Srinivas for gracing the occasion. And we will now request the external expert, Professor Vassilopoulos, to take over the stage and start delivering the lectures. Professor Vassilopoulos, please.
Thank you very much. Thank you very much, Raman, and all the speakers until now for the very kind introduction. I hope you can clearly hear me and see me, okay?
Everything is fine with this?
Yes, everything is fine. Perfect. Perfect. Thank you very much. To give a short introduction again, when you invited me this time, after 5 years, actually, I was there in 2019, just before COVID. I don't know if this caused any problems to the world. So I was there and I spent really a week, amazing week for me. It was really great. And this time that you invited me, I was a bit sad that I couldn't come because of the additional obligations that I have now here at the school. I told you that I'm really involved with a lot of administration and other things that didn't allow me to travel. So we decided to do this online course, and I said, okay, it would be an easy business because I've done it again. So the problem is that when I searched for the previous presentation, I didn't find anything. So I had to draft everything from scratch. So this is also a kind of indication. What you will see is new, is not related to what we did last time. Of course, fatigue didn't change in 5 years, so the knowledge is there. It's the same topics that we're discussing, and I will try to explain this the simplest possible to avoid any misunderstandings or any complications in the discussion. And I hope that you will enjoy. So only one thing that I would like to share also with all the participants. During the lectures, if you have any question or is there anything that you do not understand, or if you want to clarify something, please feel free to interrupt me. Do not keep your questions. Do not stay silent, as we say. Interrupt me, turn on your microphone and interrupt me and discuss to have it as more as possible by vid session. Okay? So with this, I don't know if Raman, if I need to say anything more, or I can already start presenting and then giving the...
Yes, I think you can start the presentation. The first session we are starting formally for delivery of the lectures. That is introduction to fatigue. Yeah.
Yes, so I will share then. I hope you can already see my screen.
Yes, it is visible.
Okay, so I will start. So as you said, the first lecture is introduction. Before we start discussing about the course itself and fatigue issues, I will introduce a bit myself so that everybody knows who I am and what I'm doing. I will go very, very briefly in several slides now. So my name is Anastasios Vassilopoulos. I'm currently the head, so the leading the group of mechanics of composites here at EPFL. I'm a professor here since many years. I received the title of professor 3-4 years ago, and now I'm involved, as you see, all these points here. So involvement in different committees, bodies, and so on. That's why this is also the justification for being a bit busier this time to travel. So you started, your director discussed about geography, and if you want to give a bit of geographical information here and how this is linked to technologies is where I started. I come from Greece originally. I don't know if you know where is Greece. It's not a big part of the map, huh? So that's why I say not in scale here. So I now live in Switzerland. It's not in scale. Switzerland is even smaller than Greece, huh? And I don't know if you recognize this contour in the map. This is where probably we are discussing now. So my starting point was from this city. Its name is Kalamata, and I studied in another city which is called Patras. So this is my first movement in 30 years ago, when I started studying in the mechanical engineering department of the University of Patras. Then I switched to Switzerland, where I'm now at the city that is called Lausanne. It's a bit colder than the city in Patras, but it's still nice. And now all these were physical movements. Now we are using technology to connect to a city that is called Jalandhar in India, and we are doing this online to avoid this travel this time. So this is more or less the route. If I would come there on foot, I would need almost 1,500 hours to travel. So this is another reason for the participants to pay attention and respect this distance that is in between us, which I hope it's only geographical distance. So, as I said, now I'm the head of the group of composite mechanics at EPFL. I'm working on a lot of different topics, from the material size. Probably we can go to the website and go directly to research, and there we can see that I'm working in scales from the specimen size to full scale testing of structural components, and also having objective the derivation or the design and realization of full scale structures. So the course that we will discuss, so the topics that we are discussing, are part of my experience in the last 20-25 years related to fatigue and fracture of composite laminates, fatigue and fracture of structural adhesives and joints, and fatigue and fracture of adhesively bonded joints. So these are actually the elements that we can see in engineering applications, and all the engineering applications, as we will discuss this week, they are sensitive to fatigue loading. This kind of research that I described here is the specimen and subcomponent testing, and then of course this should be applied or reflected to the behavior of structural components in different applications, and this is what we see in this additional slides here. If I go back to the presentation, I will also talk a bit about my participation here in the teaching, where we try to do some master theses that are related, of course, to composites, but in reality, we try to make them a bit more fancy, more interactive with the students. So this is a project that we did work on for the last several years, how to make composite skates. So the students understood how to design actually composite structures by doing something that it is for them it is interesting and funny. Because if you see the skate in reality, can you tell me what does this resemble? What kind of engineering structure you can imagine if you see a skate? This photo that I have on the left side. Can anyone imagine a structure that is similar to this?
The simply supported blade.
Yes. So it is a.
It's a simply supported blade with loading comes from the top.
So what kind of structure?
Thin plate structure.
Hmm?
Laminated structure.
It can be a bridge. Huh? This is a slab bridge that it is simply supported in two sections at the two ends. So this is, for example, the idea of learning by experience and by doing something which is more interesting, if you like, or more attractive for the students. So the students work on this project. We work, as I said, a lot of years on this, and we did. So you see now the process of fabrication of composites, then testing in service. So next year we continued with these projects. We had another project with students, again working with composites, and in their case they used bio-based composite materials, so composites that are taken from plants. They made this type of skate. It's a long board, we call it. You see, this is used flax fibers. So and lately, last year also, we worked on a project with students to make a composite trike, as we call it, a bike, and which at the end also we tested. So these are topics we are doing on our projects, and then these projects are linked to research that we do in the lab. Here you see, as we discussed before, a lot of research on adhesively bonded connections, of course in quasi-static and fatigue loading. And my current research projects are mainly, if you see all around here, related to fatigue and durability of composite materials, adhesives, and their joints. So this is the experience that we will share during these days. The idea is to discuss, actually we'll go very fast on this, the life cycle of a composite structure, which starts from the conceptual design of a structure, so where we imagine how we place the materials, what is the geometry of the structure. But then to realize this, of course, we need to go through several steps that are related to the material selection in the design, related to the design of the details, and then the material testing. When we talk about material testing, again, you can imagine we have material testing which is related to quasi-static loading, so to strength, but also we have material testing that is related to the durability or the long-term performance of the structural components, which is then reflected by fatigue loading and creep loading. And from the material testing, we go to the manufacturing and the design verification. And design verification in a lot of structural components is done by full physical testing, which is, of course, you can imagine it is costly and time consuming. So imagine that you want to make this blade, which might be now, today, blades are probably 100 meters long, and they cost a lot. You want to design this blade, so you have to manufacture it. You have to go through all these stages that we discussed before. You have to manufacture it, and then you have to test it. And you have to test it on quasi-static loading for strength. You have also to test it for fatigue, to simulate in the lab the fatigue loads that this structure will see during the entire operational lifetime. And what I write here, I say design verification for fatigue, because actually today we do not have methods for fatigue design. Or if we have, they are very, very scarce, if you like. They are not commonly used, and there are no commonly accepted methods that can be used for fatigue design. But what we do, we design for static. We apply safety factors that can accommodate fatigue loads, and then we do a design verification. So we apply to the structure fatigue loading that simulates the loading in operation, and we are hoping that the structure will not fail. Because if the structure fails, then we have to go back, design again, manufacture again, and do again the design verification. So you can imagine that this is very, very costly and time consuming. And what we try to do with these fatigue investigations is actually to develop methods that can overcome this problem. So to give us credibility in methodologies that can be used for real, actual design for fatigue. Of course, at the end, this is always a discussion, what you do with the material when you end the life, and discuss again about the strategy for end of life of materials, how to reuse probably the material, how to recycle if it is not possible to reuse. And all this, of course, this part at the end is now very, very interesting and very pressing, if you like, topic in the entire world. So to give you an example, how we work with structures, I will discuss about a short project. It's not a short project, it lasted 4 years, but it's a project that we had here in 2012 at EPFL, where we had to actually design a composite bridge. And the idea was to replace an old concrete bridge that was there for around 100 years over a river. Here is the Avanson River. They call it Avanson River. It's close to EPFL. And the idea was to replace this bridge that was a very narrow bridge of 1-lane traffic with a 2-lane bridge. And the commune there, the owner of the bridge, wanted to keep the abutment, to keep the infrastructure, and only change the slab. And we suggested composite bridge for the reason of the lightweight of composites. So to do this, of course, we didn't have a lot of experience at the time. So we had to go through all these steps of the life cycle of a composite material, as we said, by the selection of materials. So we investigated the potential of using wood for the core of this sandwich panel. We used glass fibers on top and bottom of the sandwich panel. We did a lot of intermediate testing for the materials. And then we ended up by designing and manufacturing the bridge, which you see it can be placed. This is the bridge actually. It's 12 meters long by 7 meters wide, and it was placed in place with a small crane. And the reason was that it was only around 12 tons of weight compared to a similar concrete bridge that would be 40 tons. So there, as I said, I will just open everything here before. We did testing from the material scale to characterize the material, to the sub-component testing, so to see the material and some structural solutions that we wanted to suggest. We did design, of course, numerical design, and then we did the full-scale testing in the lab. What you see here is a slab of 5 meters that simulates actually the entire, more or less the entire width of the bridge. And there is also a connection here in between. And the idea was to simulate this for the serviceability load and justify, this is what I said before, the design verification, justify that the bridge, the way that it is designed, can sustain the loading cycles that the real bridge will see during the operational life. And at the end, we ended up by installing the bridge in place, and believe it or not, the bridge is still there. So all this experience that I had made me, as Raman said, I don't want to talk about myself, but I just want to explain why I'm here today and I'm talking to you. Because I spent a lot of time, more than 25 years, working mainly on fatigue of composites. During these years, I supervised a lot of theses, and we have a lot of publications on this topic. Publications are in several media, from books, book chapters, the proceedings of this conference that Raman kindly mentioned before. And most of these publications, as I said, they are in the topic of fatigue and composites. If you go on Scopus and search for fatigue and composites and check the authors, I'm very top in the list because of exactly this experience that we collected during the last years. What is interesting also is that this number, we have around 30,000 documents found on Scopus on fatigue, which shows that fatigue is really an issue, and a lot of people is working on this. And if you check year by year, you will see the last years we have more than 1,500 publications on fatigue of composites per year, which means that something is moving around fatigue. People is interesting on this area, in this area. So why we are interested in this area? Because we know now, this is not a question mark actually, we know that fatigue is an issue. There is a problem with fatigue. But do we know what is fatigue? And this is what we'll try to explain today. And instead of saying here you have no idea what fatigue is, we'll try to say at the end that at the end of this course we have an idea what is fatigue. So fatigue as a phenomenon, probably you all know, is known in humans, animals, is connected to activity. If we move now we are getting tired. After an hour of teaching, we'll be tired. And this is the result of the fatigue on humans in this case. Then fatigue of materials is connected to continuous loading, again, under different excitations, that actually reduces their capacity to transfer load. So this again, if you think back to fatigue on humans, we are getting older, we are getting fatigue, damage is introduced in our body because of several reasons, because of aging, because of small accidents or bigger accidents, and our performance is degrading with time. So exactly the same happens with materials. Their performance is degraded with time. I will introduce another mention now. The nomenclature, if you want to use it, is recovery. When we get tired, then we sleep, or we sit in front of the television, and we recover, and then we can continue working or continue walking or continue doing whatever. And the same happens with materials. Most of the material, when they are unloaded, they manage to recover. So this is what we will see. How does it affect materials, and which materials are affected more or less by this condition? So give you a bit of history. Again, I don't know if you recognize this this ancient person. This was Philippides. Do you know about the Battle of Marathon? Does anyone have this? Do you know the marathon race
Yes, sir.
in Olympics? Huh?
Yeah, the person carried the news of the victory to Rome, and then he passed, and then he collapsed on reaching after sending the message.
Great, great. So it was a battle, 2,500 years before our day. It was a battle between the Greeks and the Persian army. And oops, it was the Battle of Marathon. And it was this guy, Philippides, that was actually the person that was bringing the news here and there. And they sent him from Marathon. I will just give you an idea here. They sent him, the marathon battle was in Marathon, was 42 kilometers away from Athens. So the people in Marathon were losing, Greeks in Marathon were losing the battle. So they sent him back to Athens to request for help. He went back to Athens, 42 kilometers, but there was no additional army there to join the battle. So they sent him back to Sparta. And Sparta from Athens is around 250 kilometers. And this is what we call Spartathlon. You have seen also Spartathlon. Then he came back to Athens, and then he went back to Marathon, and then he realized that the battle was finished, and the Greeks were the winners. So he came back to Athens to give the news, but then because of all this activity, he collapsed, as you mentioned. So the question here is why he managed to do all this, and then he collapsed. And the simple response, if we want to link this to fatigue, is that he did so many kilometers, so many fatigue cycles, if you want, without any stop. So we've seen, do you recognize this guy here?
Sir, Forrest Gump.
Yeah, it's Forrest Gump. You remember the movie, huh? That Forrest Gump had to run.
Version of Forrest Gump.
Yeah, he had to run and he had to go. Actually, this is what he did. He went east and west.
There was a Indian movie, Lal Singh Chadda, which was a remake of Forrest Gump. It came starring Amir Khan. So people know him.
Okay, perfect. So can you compare the race or the movements of Forrest Gump to the movements of the previous person in terms of distance?
Traveled from west to east and back, I think. West coast to east coast and back, I think. So entire America he has traveled.
Yes. So here we talk about thousands of kilometers, huh? Compared to the race of Philippides that he did 500-600 kilometers. Forrest Gump did thousands of kilometers, but he didn't collapse at the end. And the difference between, if you want to bring it again to fatigue, is exactly what he said. If you remember the movie, when they asked him how did he manage, he said, "When I got tired, I slept. When I got hungry, I ate. When I had to go, I went." So this is again a mention of what we mentioned before, what we discussed before, the recovery. Right? He was running, and then when he was tired, he was sleeping, so he was recovering. So this is exactly what happens with materials. In physical activity, we have fatigue, and then in structure, we have fatigue. structures are, airplanes, are flying, landing, rest, recover, fly again, and so on. So in all these structures that we see here, we have fatigue loads. And all these fatigue loads create different problems. So what happens when a structure operates? We have failures. And we know, I will just open this. We know that fatigue is an issue. We know that almost 200 years ago, we started understanding that fatigue is an issue. It was not an issue before, or it was not in our head before. If you see, for example, the works of Newton or all those fathers, if you want, of the mechanical engineering or the science of mechanics, they never discussed about fatigue until the middle 1800. So it's the last 200 years that we are talking about fatigue. We know that fatigue is important and we need to analyze this behavior. We know that everything fails when it is loaded. There is no infinite life for anyone. And today we have a lot of documentation that indicate that more than 80% of structural failures, independent of the material, are related to fatigue or fatigue-related phenomena. To clarify this, fatigue is a phenomenon. You can load the structure with loads that are not continuous. So, variable, variating loads, and you might lead the material to failure, the structure to failure. This is a fatigue failure. And what we mention here as fatigue-related phenomena is a failure that happens probably at a static load. So we reach the strength of the material, but the strength of the material is already reduced because of fatigue. So actually we there, and now I'm introducing some terminology, we talk about the remaining strength or the residual strength of the material. So if we imagine if we do a fatigue loading on the material and we stop the cyclic loading before the material fails, we assume that during this cyclic loading we have some damage to the material. And this damage to the material created or reduced, if you like, the properties of the material. We have reduced stiffness after this, we have reduced strength. If we do a static test at this time, we can estimate the residual strength of the material. So this residual strength usually is lower than the initial strength of the material. So you remember we said that the last 200 years we started discussing about fatigue. Why we started discussing about fatigue? Because we had some fatigue failures that were really understood and have been attributed to the fatigue loading. One early fatigue failure, as we call here, and it's also a famous fatigue failure because it started creating some questions to the mind of engineers, was this derailing of a train that was coming back from Versailles to Paris after the birthday party of Louis Philippe. Louis Philippe was the last king of France before the revolution. So the train derailed, and the accident was attributed to a failure of the axle that was due to fatigue loading. During the continuous use of the axle, there was some damage somewhere that created additional damage, and then we had fatigue failure on the axle. Then probably you heard about this, 1950s. We had the three de Havilland Comet passenger jets that were broken down during flight. Actually, the Havilland Comet was the first passenger jet without, with jet engines. And they had 3 accidents in the 1950s. And they realized at the end that the problem was due to fatigue cracks that were created along or around, if you like, the rectangular windows that they had on the plane. So they redesigned at the end the window of the plane, and that's why today you know we don't have rectangular windows in planes. We had also this failure of the Liberty ships that failed during the Second World War in the ocean, when they were changing from hot climates to cold climates because of again fatigue cracks that nucleated at the corners of hatches that were designed in the bridge in the ships. We have this famous failure of the Aloha airline flight in 1988. I don't know if you have seen this again, but it was a quite amazing or impressive failure, if you like. During flight, there was a crack that initiated in the connections, and this crack propagated rapidly and ended up to actually destroy the plane. I will show here, and then I will come back to discuss why. So so you see that it was, let me show, this is how the plane ended up. The plane opened completely because of this crack. So the post-mortem analysis showed that, I go back here, that the failure was due to fatigue because the plane has been designed for 20 years of lifetime. And during these 20 years, the design was supposing that the plane will do 75,000 flights. What does it mean? A flight for a plane is actually a pressurization and depressurization. So it's a fatigue cycle. So in this case, the plane, since it was used in Hawaii, it was doing only short flights. And during 19 years of service, it already exceeded, you see, it did 89, so almost 90,000 flights instead of the 75,000 flights of design. So it exceeded actually the design lifetime. And what I have a short video here. The flight started. And during flight, just moving a video a bit faster. So during flight, you have a crack, and then parts of the plane were taken out. Fortunately, there was only one casualty, a steward lady that was not attached with a belt. All the other passengers managed, together with the pilots, to land safely. So the plane continued flying like that. And I'm just moving a bit fast. Landed. This is video now. This is real video from the plane. The evacuation procedure. So actually the plane ended up like that. So we see first of all the effect of fatigue loading, the disaster that we might have, but also here you see the redundancy of engineering structures. A plane managed to fly without part of the fuselage. We have other problems in other structures. The capsizing of this offshore hotel because of a damage in one of the bracing arms here. And you remember when we discussed about the first failure, it was in 1852, 200 years ago. And now in 2017, we still have the same failure. It happened in Australia, where an axle of a train has been also broken because of fatigue that initiated and propagated in the axle, in the metallic, the steel axle, due to fatigue loads. So, Raman, do we need to do a break or we continue? I'm having I don't know what is the timing for you.
We can have a break as per your convenience. Maybe we can have a break for 5-10 minutes. And
Okay.
then we can
Let's do then 5 minutes break or 10 minutes as you wish, and then we can come back.